Hey time travelers. Alright, this video is going to be on like 1D motion and graphical representations. I know that the main like focus in your physics like thing like day one is just 1D motion. So I am going to hit on that, but I think the much more important like physics concept is graphical representation, which is like how do we model these systems just like either in a visual or through a graph, that type of thing, because I think understanding that is a lot more important than just like, it's basically the why behind the like what we're doing with 1D motion. We actually kind of did 1D motion yesterday in this, so I'm just gonna reuse that because I think it hits on a couple of key things that you should like be able to do per se. Okay, one of the most common problems that you'll see is like a ball rolling to a stop, or like I've seen like a penguin speeding up as it goes down ice. I will do that one because it touches on an important topic. If you're ever given a physics problem, more often than not, one of the best first steps is just to make a very simple diagram. So for example, if I am told just from the problem, like a ball is slowing to a stop, I'm told that it goes over 4 seconds, like over the span of 4 seconds, it goes from 2 meters per second to rest. You can see this all in this piece of like thing, and you just mark in 2 meters per second and rest. The reason this is important is because for much more complicated systems, you will be able to keep track of a lot more things that are going on, and it will often catch you from making like silly mistakes. So more often than not, you'll be given like words and you'll be asked to create a like sort of graphical. And also, sorry, I feel like this is a lot of alsos, but also it's just sort of like a test of knowledge of, do you know like what is going on? Again, that's like really important in the context of like, hey, are you about to make a very silly mistake just because you aren't thinking like quite right? Another thing that I have found it helpful for is there's a lot of memes of like me when I calculate that the rock is going negative 12 seconds per meter, right? Like obviously that doesn't make sense. Having a sort of graphical can help you either explain the answers that don't make sense at first, or it can make you go, wait a minute, I have to have made a mistake somewhere. Let me check my work. All to say, you will probably be asked to make a graphical, and it's also just an important physics skill to have. All right, so I don't think you'll see much more complicated things than this for 1D motion, but I do want to talk about graphical representation because this is not just important for physics, but I'm sure it will come up in any sort of standardized testing that you ever have to take ever, which hopefully we're done with that now that we're in college, but you never know. Okay, so there's 3 types of graphs that you will probably be asked to interpret. One is a position graph, one is a velocity graph, and one is acceleration. I'm gonna be honest with you, you're probably not going to see a position graph like this. You might see a velocity graph like this, and you probably will like certainly see an acceleration graph like this. And that is because in every intro physics course, acceleration is always constant. Velocity graphs, you might get something like this, or you might like get something like this. And if you get something like this, you'll probably be asked to interpret the acceleration. Now, what's really nice about all of these graphs is that they kind of inform each other on the basis of slope. And that is to say that if this is at 2 meters per second squared, that this the slope of this is 2 meters per second. And that is to say, at 1, this value is 2. And that's what's like really nice about these graphs. And likewise, like if you know that this is at 2 meters per second, you know that the velocity here is 2 meters per second. And that's the change in position at that time, right? Because your change in position over time is your velocity. Your change in velocity over time is your acceleration. And that's just sort of like graph theory that if you, these are all, like position against time. These should be time. I'm not very good at graphs. Don't at me. I think one thing to note is that you will probably be asked to sort of show like what this could be showing. So for example, let's say we are given a position against time. So that's this first one. And we're told that something moves forward, stops, moves backwards, and immediately comes back. And then once it's back, it's back. We could say that a child at initial conditions has a ball and kicks it to another child who kicks it to a third who kicks it back. And we could say this is how we're measuring our x. We kick it forward, we kick it backwards, and we return it back. I was always taught to write IC for initial conditions if I have something that I know will change over time. I honestly, I would be okay if this is your like graphical representation again, because your graphical representation is only meant to like, or your like image representation is only meant to like aid you in your understanding. And I think that this is like fine. Now you might be asked to like represent the velocity of the ball like across these times. And I wouldn't put it out of the question to say you might be given one graph and asked to draw another. Usually you'll only be going this way, where you'll get the position and then you're asked for velocity, or you're given the velocity and you're asked for acceleration. Usually you're not asked to do the other way around, because it can get a little bit messy. So here, the velocity, we have it going forward as we kick it to the first child. Then it sits there with the child for a little bit before it's kicked to the second child. And then it's kicked back. Oh, shucks. Sorry. It's kicked. Sorry, I'm like lining it up. It's kicked back, and then it's just at rest. What's kind of a little bit hard is that these graphs will be discontinuous more often than not, especially if it's like it's not straight. But that is just kind of how it goes sometimes, right? Like this is an accurate graph for what happens. It's kicked forward at a constant velocity. It stands there, it's kicked there, it's kicked back. Obviously, for acceleration against time, these have a slope of 0 meters per second because we're saying it's not slowing down. So it's just going to be 0 all the way through. Even though velocity does change, we don't really consider instantaneous acceleration. At least I have never been had to do that. Okay. So that's my little spiel on like graphical representation. I'm gonna do a physics problem, which just kind of shows why graphical representation is important and how seemingly complex things might be 1D motion. Okay, I would like to preface with this is not always going to be the case for motion which is happening in both the y direction and the x direction. But we can say that this penguin, which is on ice, penguins on ice, get really familiar with them. They're going to be a very popular physics demo that I have, because they model everything with constant acceleration. If we draw like a motion diagram, we can tell that we are speeding up. And also, we can tell that this is on one dimension. That if we were to track it across this, we are speeding up constantly in this direction. And so what we can do is we can say, even though there's the x direction and the y direction, a neat physics trick is that we can just consider this a new plane. We can say that this is the x direction. And the way we do that is we write our own coordinates. We say we are marking this as the x direction and this as the y direction. And by doing that, we are setting it to be this. And we just have to be consistent about that. And no laws of physics breaks down when you do that. Everything is okay. So by doing that, you can make a complex problem into 1D motion. And another thing is that when you're given this graphical, you're able to see like how, or like what variables you do and you don't have. So for example, we're given velocity, we're not given time. We are given that it's over a period of time which spans 20 meters, but you don't know that. So you know final velocity, you know initial velocity, and you're trying to find acceleration. So we can say one of our handy dandy kinematic equations, final velocity squared is equal to... Okay, I just had to double check that I had that right. We just need to rearrange for acceleration. There's no substitution that needs to be had. This works. And so you get 1/8 meters per second squared. And so that's why like modeling is important, because you can take things which normally would be pretty complicated because you have a y component and x component, and you rearrange it so that way you have more simple motion, which you can just find the acceleration for. One thing to note is that this vector is in this direction. It's in the x direction. Or what we have marked as the x direction. And so that's one thing to like make pretty clear, is that you are saying this is in the x hat direction. I think that's kind of all. Like this is kind of the extent to like a physics like application that I can think of. Yes, good luck time travelers, you've got this, I believe in you.